Hi everyone, today we're going to take a look at yet another Keithley digital multimeter. This time it's the model 178. These were manufactured around about 1978-1979 and were one of a range of meters that Keithley produced at that time that used a chipset which was specifically designed for 4.5 or stroke 3.5 digital multimeters. This chipset was manufactured by Intersil and was used by many other multimeter manufacturers at the time. So rather than go through all the function buttons and range buttons at the front, which are very similar to the other meters I've discussed in my previous videos, what we'll do now is we'll take this apart and have a look inside and just go through exactly what the changes are. Right, like all the meters of this type from Keithley, the dismantling is exactly the same. We have the 4 screws underneath the meter, and then the top part of the case comes away. So I'll just quickly remove these. And the top cover just comes away. I'll just remove the tilting bail. Right, what we see inside the meter. This is interesting because this particular one does actually have the rechargeable battery pack on the top, which is an optional extra. I'll just remove that for the moment and we'll have a look at that in more detail later. So to remove the battery pack, we simply plug it from the back and then it should just lift off. There you've got the earthing spring there, earthing the metal here of the battery pack. So there we have the battery unit. It's a self-contained unit. I'll put that to the one side for the moment. Right, now we have a look at the main PCB of the meter. Right, I'll just turn the meter around so we have a clearer view of the printing on the printed circuit board. Right, we have the spacers here which need to be removed as before, so we'll just remove the spacers. There's the earthing clip. Right, I should now be able to remove the whole printed circuit board, but before I do that I just need to unplug the mains lead. We can now lift the whole module out, and I'll put the case to one side. There you have the front panel. This comes away. Just leave that there for a moment. And what I'll do now, I'll just zoom in and we'll have a closer look at the printed circuit board. Well, I think you can see straight away that this particular board is much simpler than some of the earlier multimeters that Keithley produced, and it's all down to these two ICs here, which are a pair produced by Intersil specifically for digital multimeters, and they contain the bulk of the circuitry for this particular board. The ICs here in question is the ICL7103A and the ICL8052A. Those are the two main chips. Here you can see we have a crystal, quite a large looking crystal. This is actually a 100 kilohertz crystal. I'll come back to the reasons why for that in a moment. And we have a logic IC here, part of which is being used to form the the crystal oscillator circuit. Here you have some preset resistors which are to do with the calibration of the meter, as is the variable capacitor there. There you have a DIL resistor network, and these white items running down the middle of the board here are actually 5-volt read relays which are used for switching the ranges, the resistances for the ranges of the meter. And the resistors in question are all high tolerance resistors. You have the two here, and you have a group here. You see the black ones here are high tolerance resistors that are used in the input switching circuitry. There you can see we have an op amp. That is the main op amp on the input of the meter, and that works in conjunction with the switching circuit here, adjusting the gain of the operational amplifier for whichever particular range that you happen to be on. In this part of the board we have the voltage reference source. This particular meter again uses a temperature compensated Zener and operational amplifier there, giving a constant current source for the Zener, together with some high tolerance resistors, and that's used to generate the reference voltage for this particular meter, which is required for this particular chip over here, the main chip of the board, and it requires a reference of 1 volt. So although they're using a 6.3 volt Zener there, 6.4 volt Zener, they have to then convert that down to 1 volt reference to supply the digital circuitry of the meter. At the back of the board here we have the power supply arrangements, mains transformer. We've got 2 bridge rectifiers here. The small one is being used for the plus and minus 15 volt ranges, and the larger current one there is being used for the 5 volt plus 5 volt range. There you can see the 5 volt regulator IC, associated capacitor, and on the other side of the board there in the corner there is the large one there is the plus 15 volt regulator, and the small one behind it is the negative 15 volt regulator. Here again we have some trimming pots there used for the calibration of the meter. Okay, we'll zoom in a little bit closer. I'm particularly interested to have a look at the voltage reference circuit here, so I'll zoom into that area first and we'll have a look at that. Right, there we can have a closer view there of the voltage reference source circuitry. Around that area you can also see we have some test points for the negative 15 volt and the plus 15 volt supplies. That's quite nice. And the test point 3 you can see there is actually the test point for checking the actual reference voltage of the Zener. There's the Zener, which is a 6.3 volt or 6.4 volt Zener. So we can check the voltage at that point there, test point 3. All of these high tolerance resistors here are actually to do with the voltage reference circuitry here. And we have some strange values actually, because we're looking there, we have a 3.65k resistor. The next one there, looking at that, is a 6.49k resistor. There's the Zener, which is the 1N4577, temperature compensated Zener. And then we have another high tolerance resistor there, which is an 806 ohm resistor, and then another one there which is a 402 ohm resistor. Now these two here vary from meter to meter, and they're actually chosen during manufacture, and they select specific values to ensure that they get the correct reference voltage. The chip there is basically it's a 741 op amp, which has been used to ensure that we have a constant current source for that Zener, which keeps the whole things very, very stable. The Zener itself has a temperature coefficient of somewhere around 0.002%, plus or minus 0.002%, so quite high. But by using a constant current source, you can actually improve the stability of the Zener reference there. The output from this circuitry is then divided down by the resistor networks here, and then trimmed by this 15-turn pot, it would appear, on the back of the meter. It's got accessible through the back of the meter, and we actually adjust that for a reference voltage for the multimeter of 1 volt exactly. What we might just have a look at now, we'll have a look at this circuitry, just have a look at a schematic of that and just to understand how that's achieving the reference voltage. Right, here we have the circuit of the voltage reference source for this meter. There you've got the operational amplifier, the 741. There is the temperature compensated Zener, the 1N4577, giving us a 6.3 volts there. And that's the driving resistor for the Zener, the 806 ohm resistor there. That's giving around 3 milliamps of current for this particular Zener. You'll notice here that we have a potential divider, and they've selected very accurately those resistors there, 3.65k and a 6.49k, and that's setting this voltage on the negative input of the op amp at around 6.3 volts. It's taking it from the output, which is running just around 10 volts, maybe just a fraction under 10 volts. Dividing it down, we're getting 6.3, and the reference voltage is going to the positive terminal of the op amp there, so that's also at 6.3. And if you remember, the way that operational amplifiers work is that these two input voltages will always try and come back to match each other. So if for any reason any one of them tried to go high, the other one would bring back and match it again. So what happens here is that these two voltages are held stable, and if these two voltages don't change, then the output voltage is constant, and if the output voltage is constant, that means that the voltage supplying the source resistor for the Zener diode is also constant, which implies we have a constant current source going through that Zener. And that improves the accuracy of this reference voltage now to anything up to plus or minus 0.001%. So it virtually more than doubles, or at least doubles, the accuracy of the temperature coefficient of the Zener there. What they then do here, you can see we have a potential divider network here, and they're tapping off 1 volts, which is the reference source for the multimeter. That is trimmed by this preset here, R113, and during manufacture these two resistors are selected for that particular meter, and these depend really on a number of things. Obviously it depends on the accuracy of the other resistor here, but the most important thing is that the Zeners do vary slightly, so they're trimming these to ensure that they can actually tune this down to 1 volts precisely and give some range on that potentiometer there. So there we have it. That's the circuit of the voltage reference source, using that op amp to fix the source voltage. If the source voltage is fixed, then the current is constant, so we have a constant current supplying that Zener, maintaining a very high stability. Here we have a graph of the characteristics of the Zener diode that we're using. Down this side here you can see the temperature coefficient in percentage terms, and along the bottom here we have the operating current. You'll see here that the nominal operating current of 2 milliamps should give you exactly a 0 temperature coefficient. Increasing or decreasing that current will affect the compensation. Keithley appeared to be running the Zener at around about 3 milliamps, somewhere here, and that's giving a potential error there of 0.002%. Right, here we have a closer look at the main part of the multimeter itself. These are the two main ICs, the ICL7103A and the ICL8052A. These work in conjunction to provide the output for the LED display on the front panel. Basically, they have all of the circuitry in those two chips. This includes analog to digital conversion using dual slope. They have such features as auto zeroing in the chip itself. This particular IC here, the smaller of the two, does in fact have built in a reference voltage source of 1.75 volts, which could be used as the reference for the meter. But Keithley have felt that they wanted to improve the accuracy of the meter, so they don't actually use the voltage reference source in this chip. Instead, they generate their own voltage reference to a much higher standard and therefore improve the accuracy of the meter. The chip itself here contains all the multiplexing, the BCD outputs and the digital drivers for the LED display on the front panel. There's the 100 kilohertz crystal for the clock. The reason Keithley selected 100 kilohertz is that in order to achieve the maximum rejection at both 60 Hz and 50 Hz mains frequencies, what they have to do is have a crystal frequency which is a exact multiple of both those two frequencies, and 100 kilohertz is just that. There is a number of other combinations as well, but they've selected the 100 kilohertz. This allows the meter to do 2.5 readings per second. Right, here we can see the front digital display board of the meter. Here we have 4 7-segment LEDs, and then we have sort of a half segment there for the last digit and the symbol of the plus or minus. On that side of the board we have a 75492, which is the LED driver chip, and on this side we have a 4511, which is a BCD to 7-segment decoder chip, and this blue DIL package here is the resistor network for the LED display. The whole module there can be unplugged. You'll see at either side we've got 2 plug connections, so you could actually remove this whole board quite easily. Alright, well that's that. It's quite simple, nothing complex there. Just a couple of points to note here at the back. This slider switch here is the mains selection switch for the mains transformer, either 115 volts or 230 volts, and that's the socket for the battery pack, and next to it you have the switch which can switch either battery pack in or with battery pack out. If you don't have a battery pack, you have to have the switch in the line position, which is in this direction. With the battery pack in, you need to switch it the other way. In this corner of the meter we have the zero adjust preset, which is accessible through a slot in the front panel. That's just below the input connectors. Okay, let's have a look at the circuit for the battery pack. The pack The option is 1788. It uses 4 2-volt D-type cells, each rated at 2.5 ampere hours, and the total cells that are all in series is fused with a 2 amp fuse. When the meter is switched to use the battery pack, the slider switch on the main printed circuit board is switched to BAT for battery, and then what happens is that the voltage that would normally go from the bridge rectifier here to feed the 5-volt regulator is disconnected, and instead the voltage from the bridge rectifier is fed directly to an SCR, which is used as a switch. That SCR is turned on and then supplies the DC voltage to charge the battery cells. The SCR switch there is turned on by another voltage which is derived from the rectifier, which would normally provide the 15-volt supply. And what we're doing here is we're taking off from the positive side of that rectifier, from the 15-volt supply rectifier, and we're feeding it through a resistor there and a diode to turn on the SCR. So in other words, once the power is switched on and you have voltage coming out of both bridge rectifiers, the SCR would normally turn on and supply the DC voltage to charge the battery pack. The battery pack would then normally charge to a float voltage of around 9.8 volts, at which point you want to switch off the charging current. That is achieved by turning off or removing the voltage to the gate of that SCR, and that's done by this transistor here, which it has a Zener diode there feeding its base. The Zener diode there in question is an 8.2 volt Zener, and that's forming then a potential divider down to chassis, which is then tapped off to the base of that transistor, and that is adjusted to a level where it would normally turn on the transistor. It would then ground the anode of that diode and remove the DC voltage to the gate of the SCR, switching the SCR off and removing the voltage charge supplying the battery. This particular resistor here, preset resistor, is adjusted at the factory at manufacture, and normally it's not needed to be adjusted thereafter. It's set to ensure that when the battery reaches that nominal level of 9.8 volts maximum, that this transistor turns on, removes the bias from the gate of the SCR, switches the SCR off, and removes the charging current to the batteries. As the batteries start to discharge, the voltage drop. As soon as the voltage drops, this transistor here switches off and the biasing current for the gate of the SCR is restored, and switching back on the charging current. The other protection we have for the battery is to prevent the battery from discharging to a low voltage which could damage the battery long term. So what we do here is that if the battery gets to a voltage less than 7.2 volts, we remove the battery from the meter. So we switch off the battery. This is achieved by a voltage supervisor chip there, which is an ICL8211, and that's connected straight across the battery supply. Pin 3 of that IC is supplied with a voltage which is determined from the battery, so you have a potential divider there, and it's such that when the voltage on pin 3 reaches 1.15 volts, then this IC gives an output on pin 4. The output on pin 4 then grounds that resistor there and turns on this transistor here, which is a PNP transistor. When that transistor is turned on, it shorts the base and the emitter of the Darlington pair transistor there and turns that transistor off. thereby disconnecting the battery from the 5-volt regulator. This circuit here is the DC to DC inverter, which is actually used to generate the higher voltages for the minus 15 and plus 15 volt supplies, and that is achieved by these transistors here, and they're fed with a clock signal coming from a D-type flip-flop. Here you can see a D-type flip-flop, it's just switching and acting as a normal DC to DC inverter. The main difference to this circuit compared with some other inverters is that the signal sent to this D-type flip-flop is coming from the clock oscillator of the meter, which, if you remember, is 100 kilohertz. So that the switching for the inverter is switching at 100 kilohertz, which is exactly the same frequency as what's used by the analog to digital converter and the logic circuits on the meter. And the reason they do this is by synchronizing those two frequencies to be the same frequency. It removes the noise effects from the inverter affecting the overall performance of the meter. Here you can see the AC output from the inverter then being rectified by these two rectifiers here, these two diodes here, and then being smoothed, and then those positive and negative voltages, the higher voltage there, are fed to the plus and minus 15 volt regulators to then feed the 15 volts to the main printed circuit board. So there you have the battery pack circuit, which is actually used on a number of the Keithley meters. So you'll see this circuit used on several Keithley meters of this sort of same vintage. Now if we have a look at the layout of the battery pack, here you can see the 4 D-type cells, 2 volts each, and they're all lead acid cells, these. There is the charger module and the control module for the battery pack. I'll just pick out the main components. In that corner there we have the SCR, which switches the charging current on to the batteries. There we have a 4013 IC, which is 2 D-type flip-flops, which are used to control the inverter part of the board. This part of the board here, we have the inverter, which is the DC to DC inverter, and basically what that is doing is providing a higher voltage output to feed the plus and minus negative 15 volt supply regulators. So here you can see the transformer for the inverter. There's 2 small power transistors which are driving the inverter, and then these small transistors here are the ones that are controlling these main drivers that are switching the transformer. In this area here you have a small IC. This particular IC is a voltage sensing IC. So basically what that does is detecting the output voltage of the batteries, and when the batteries, as I mentioned, go low, below a certain level, it then disconnects the batteries from the meter. This small transistor here on the board is the one that controls the SCR and can turn off the SCR if the charging current to the batteries has reached its maximum. Well, I hope you found that teardown of this Keithley 178 multimeter useful, and I'll see you all again next time. Bye for now.